Everybody, welcome back to another fun and exciting geometry class. Today we're going to be talking about some new concepts. Really all of them are based on the idea of location, or if you look down here at the screen, we'll just jump right into it. It's not in your book. I'm just going to kind of give you this definition. It's in your book later, but I think it should be right here. So I'm going to tell you the definition right now of loci. Okay, loci. Now, this is not the Loki, the guy from the Marvel superhero shows, okay? This is loci. Loci stands for, or it's kind of like a short for location or located. You see the very first part of the word there, loc. And so in that definition, you'll see it is the collection of points that satisfy a given condition. So if I say the number of points or the points that are equal distant from another point. Okay, so that would be a loci because there's a condition that it has to meet. It has to be equal distant. Well, we're going to be on page 107, so you can open up there. And with that kind of basic definition of loci or location, we're going to talk about some location theorems. So if you'll go ahead and look down there, we're going to start with theorem number 27. There's two parts to theorem number 27. I have it down here on the screen in front of you. It says every point in a perpendicular bisector is equidistant from the ends of the line. Every point in a perpendicular bisector is equidistant from the ends of the line. So there's your qualifications, there's your parameters, and so every dot, every point is going to end up making our line. This is a loci or a location theorem. All right, and then the B part of that, the second part of that, is that the converse is also true. Or in other words, so this one says that every point in the perpendicular bisector is equidistant from the ends of the line. So you could also say that every point equidistant from the ends of the line is a perpendicular bisector, basically saying it the same thing, only saying it in reverse. So let's see what that means. Here is a diagram that I have drawn for you. And it's not perfect, I didn't measure this out, but I just want you to think through it. So if we take our points here at the end of this line right here, okay, so we'll call this A and we'll call this B. Every single point, these purple points right here, okay, every one of them counts in to make up a line. We could keep adding points and points and points and points, and pretty soon what would we have? We would have a line that goes up there. And if we did the same thing on this side, we would have a line that goes down there. Well, one thing about those points is every one of those points, let's take for example this third point right here. This third point and this third point are equal distant from this line right here. This line ends up, let me just kind of erase this right now. This line ends up becoming a loci, a collection of points that are all equidistant from the other collection of points. What do we have? We end up with a perpendicular line. Okay, so let's say that this is 7 and this is 7. And then obviously the farther up we go, this would be smaller. So this is 3 and this is 3. But the idea is that every single, as far up as we go, every single one is equal distant. This one would obviously be a little bit longer. You know, this one might be 9 and 9, for example. It's almost like the idea of a Christmas tree. It goes up to the point, but the perfect Christmas tree would be symmetrical all the way down or equal distant from the center of the tree. In this case, the center of the tree would be the perpendicular line that goes up from that line. So that's what that theorem is saying, theorem 27. All right, let's continue on. Let's look at corollary 27.1. 27.1. I don't have that one written down for you to look at, but as I'm reading it, you can be looking in your book. It says 2 points, each equidistant from the ends of the line, determine the perpendicular bisector of that line. So in other words, if we go through this and we keep going all the way up, basically what I've already said, it forms this perpendicular bisector right there. So I just kind of combine those in my explanation. All right, theorem number 28 is on page 108, theorem 28. And it says that all points in a bisector of an angle are equidistant from the sides of the angle. And then the converse is also true to that. What does that mean? Well, that means that every point equidistant is a bisector of the angle. All right, so let's take a look at the angle. And so if I have this line right here as my bisector of my angle, if you take these yellow lines right here, these yellow dots, if you keep putting dots in there, you end up making a line. Well, if you start at this point right here on your this loci, okay, you would find that, okay, this is 3 and this is 3, the distance. Well, if I did the same thing out here, this would be equidistant as well, and this would maybe be 6, and this would be 6. If we keep going, we're going to keep doing that, and this would be 8, and this would be 8, for example. But what happens is we keep putting points, and pretty soon, when we keep putting points and points and points and points, we end up with a line, okay? And so it forms our bisector of that line. So that's called location. The location of those lines is being dictated to us by the conditions that it gives us. The condition is all points that are bisectors. So if we take this bisector, so all these points that are bisectors, they will be equidistant from the edges of the angle. They have to be. Okay. All right, and you're probably sitting there thinking, yeah, that makes sense, okay? Because if it's a straight line, if it's bisecting the angle, cutting it in half, then we're cutting the distance in half all the way. And if you cut something in half, both things are equal on both sides. Okay, let's see, what else do we have? Let's look down at theorem number 29. This is on page 109, page 109. I'm actually going to be doing 3 lessons in this video, so sometimes these geometry lessons are pretty short, so I like to just kind of stack them all in there and not do a separate video for each one. So this is 2.24, concurrent lines. Okay, so theorem number 29 says the perpendicular bisectors of the sides of a triangle meet at a point that is equidistant from all 3 vertices. The perpendicular bisector of the sides. So if we go down to a triangle, I've got one down here, and if we take the bisector of this line, so that is bisected right there at that point, so maybe this is 4 and this is 4. In other words, we're cutting that line in half, okay? And if we make the theorem says, if we make a perpendicular bisector at that point, okay, so if we draw a perpendicular line at that point, and then we go here to the next side and we do another perpendicular bisector at the midpoint, okay, and then we go here to this side of the triangle and we make a perpendicular bisector at that point. All of these lines are going to meet. Look at this point right here. They all meet at that point. That point is called something. It's got a name. And that name is the circumcenter. The circumcenter. That word is in your book on page number 110. Right there. It's called the circumcenter of the triangle. Making the middle of a triangle is very hard. So like a middle of a circle is easy. You just draw a circle and then right in the very middle there's a dot. Well, okay, that's the center of the circle. But trying to figure out what's the center of the triangle. Well, it's hard because it's like, what do you mean the center? The center of the angles, the center of the sides, the center of what do you mean the center of? Okay, so really triangles have 3 different centers. The first center that we're learning about right here is the circumcenter. The circumcenter is when you bisect the sides. Okay, so let's write that down there. Circumcenter is bisect the sides. Okay, with perpendicular lines. Okay, when we bisect the sides with perpendicular lines, we cause it to, or the point that we create is called the circumcenter. Now, I wrote another word up here that you might have seen while I was talking about that called it's concurrent lines. Concurrent lines. The definition of concurrent lines is on page 109. Three or more lines that touch. So, there's a line, there's a line, there's a line. When they touch at a certain spot, at a vertex, those are concurrent lines, okay? And they can be whatever you want, okay? But they have to touch at a common point. That common point is called a vertex, and those three or more lines are called concurrent lines. So these three lines right here are called concurrent lines. So whenever you hear me use the word concurrent, that's what I'm talking about. Okay? All right, let's keep going with this. This is on page 110 of your book, so you can look at page 110. And that's where you find circumcenters on page 110, by the way. Now, something interesting about this right here, if we go back here, if we were to put a compass on this, and we were to put a compass on this point right here, the circumcenter, well, something really cool would happen, and we would get a, circle that touches all the points. I'm going to try to do this. It's not going to be pretty, but if you'll give me just a second. Okay, now that's not perfect, but this is an idea of a what they call an inscribed triangle. Okay, look at the triangle. It's inside of the circle and it's touching the circle with all of its points. This triangle is inscribed, and the word there is in your book, inscribed. Now, the other thing that we have is if we're talking about the circle is what's called circumscribed about the triangle. So in other words, the triangle was there and then we circumscribed or put the circle on the outside. So if it's on the outside, if we're talking about the circle, which is on the outside, it's called circumscribed. If we're talking about the triangle, which is on the inside, then that is inscribed. Okay, so inscribed inside, circumscribed on the outside. And that is the circumcenter. Okay, the next one is called the Ortho Center, and that is on the bottom of page 110. The bottom of page 110, that's corollary 29.1. And what we find here is that if we take the three altitudes of the triangle, so what is an altitude? Well, an altitude is the distance from the peak of the triangle to the base of the triangle, and it's a perpendicular line. Now, notice that that is not in the center. I didn't bisect the side, okay? I just drew it from the peak to the side, and I made it into a right angle. In other words, that's a right angle right there, okay? Now, I would do this with every single side of the triangle. Okay, there's another one. There's my right angle right there. Okay, so I've made my right angle perpendicular, and I've drawn it to the top. That's an altitude. So I've got one more side here, and notice when I connect this one, it makes another point. This is called the ortho center. Okay, and so the ortho center is created. Okay, there's the ortho center. It's created when you have when you join the three altitudes. Okay, so I take the three altitudes, I draw them, the place where they join, the place where they connect. This right here is called the ortho center. The ortho center. All right. Now, something interesting about the ortho center is the word ortho comes from the Greek, and the Greek word there, ortho, means straight. All right, so I don't know how important that is to you, but if you've always wanted to know that, now you know. And so ortho center means straight because these lines are all straight lines. Okay, and they create the ortho center of the circle. All right, the next one, Theorem 30. When you bisect the angles of the triangle. All right, so now we've got another triangle, and now I'm going to bisect the angles. Now I'm not worried, in this one, I'm not worried about cutting it in half. I'm not worried about bisecting the sides. I'm not worried about altitudes. In this one, I'm focused on the angles. So I want to make sure that that angle is bisected. Okay, so let's come over here and let's bisect it. I'm just kind of coming close. You would do a more accurate job with your compass and you remember how to bisect, hopefully. Okay, that one is giving me problems up there. I don't know what's wrong with it. Okay, so we'll go ahead and bisect this one. And then we will bisect this last angle right here. And the place that they join is called the incenter, right there on the bottom, incenter. Okay? And that one, to me, it sounds the most like the center of the circle because it's the incenter. And let me tell you why they call it the incenter. This one's interesting because something happens right here. If you take your compass on this point right here, and if you draw a circle here, now mine's not perfect, but it's pretty close. If I had a protractor and if I had a compass, I could measure it and I could get it better, get it perfect. But I'm just kind of drawing it with my drawing program here on the computer. But what I want you to see is this incenter right here. Okay, where these come together, this point right here is the center of the circle. Now it's not perfect, and you can see that when I draw that there. But if I was drawing it right, it would be the center of now look at the difference. So if I go up here, now my triangle is inside my circle. Okay, that's inscribed. Now look what I have. Now I have my triangle circumscribed. Okay, and so now my circle is inside. Up here earlier when we were working with the circumcenter, my circle was on the outside. Now that we're working with the incenter, my circle is on the inside. Okay, so the incenter of the circle, and I've been writing this down so you can write this down with the incenter. The incenter is when you bisect the angles. Bisect the angles. Okay, and that will give you the incenter. These are all very, very important for you to know. So make sure that you study these, you learn these, but they all are very important. All right, the last one that I want to show you is on the bottom of page 111. The bottom of page 111 is Theorem 31, and Theorem 31 says, I've got it written down right here, the three medians of a triangle meet in a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. Well, that's a lot of words. What does that mean? So if we take the medians, okay, what is the median of a triangle? As mentioned, the book says, as mentioned in section 1.10, so you could go back and look there. The median of a triangle is the line drawn from any vertex to the midpoint of the other side. So we are drawing something from the vertex to the midpoint, vertex to the midpoint. Then we could put another median in there. And so let me put this in yellow. So these are the two triangles that we're talking about. That triangle and that triangle. All right. Now, if I put the next one in, now we're talking about this triangle and this triangle. This is the median of the other side. This is a second median. And then I'll use this one. I'll put this one in pink. Let's actually use a line here. Here we go. Now we're talking about this triangle and this triangle. Okay, so these are three different medians of the three different sides or of the three different angles. But notice they create a point right here. Okay, they create a point right here in the middle. And those are called the medians of the circle. And notice that the medians of the triangle meet in a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. And we're talking about the blue line. This blue line, this part up here is the 2/3. This part down here is the 1/3. If we're talking about the yellow line, this part right here is the 2/3. This part right here is the 1/3. On the pink line, this part right here is the 2/3, and this part right here is the 1/3. Okay? And that's what that theorem number 31 means. All right, well, I know that was a lot of stuff. It was a long video. I hope you hung in there and did your best to pay attention. Lots of material. Make sure you go back, review, and those things are going to show up on quizzes and tests in the future. So work hard, study, and if you have any questions, just rewind the video and watch the part that you struggled with, okay? All right, we'll see you later. Have a good one. Bye-bye.